Now I am recording. Thanks. Hello. Oh, now apparently when you zoom in even further, now you can start to tell the difference on this, which is sort of defeating my point, but that's okay. All right, so the idea is we'll use if maybe we don't know everything about a function, but we know its rate of change at a certain point, and we'll use that to basically approximate the function near that point. So for example, say we have this function f of t, which is the cost to heat a room in dollars per day. All right, where T is the outside temperature in degrees Fahrenheit. And we know that F of 23 is $2.10. So basically, when the outside temperature is 23 degrees Fahrenheit, it costs $2.10 to heat the room per day. All right, the derivative of this function at temperature 23 is negative 0.05. All right, so it's good. It can be good to look at the units. So F of t is measured in dollars. The derivative is measured in dollars, so it's like change in x, change in y over change in x, right? So the function itself measures dollars, but the variable, the independent variable, measures temperature. So this will be sort of change in dollars per temperature, or degree Fahrenheit. Okay. Yeah, essentially, Matt. Yeah, that's basically the answer to part A. What is the practical meaning of the fact that f prime of 23 is negative 0.5? So this is saying that when the outside temperature is 23 degrees Fahrenheit, then the cost to heat the room is decreasing by approximately 5 cents per degree increase. Okay, and this should make sense that as the temperature increases, the cost to heat the room decreases. All right, so let's use this. Let's use this then to approximate the cost to heat this room when T is 20. Okay, so why don't y'all take a couple minutes? I won't break y'all into groups yet. But why don't y'all take a couple minutes to try to answer B? Like, how would you approximate using this data, the fact that at when it's 23 degrees, it costs $2.10 to heat the room, and the derivative, so this is a rate of change, is negative 0.5, basically per degree, or negative $0.5 per degree. Try to estimate what it would cost to heat the room when the temperature is 20. Hello. Okay, give me one sec. I need to make my clone a moderator. Sorry for the matrix going on there. Did it work? I cannot tell. Okay, it did work. All right, so I can go back to this other screen. You should be able to hear me. Yeah, that's true. It's going to be a ban in the chat. Yeah, Matt, you're moving in the wrong direction. So remember that the derivative is negative, but 20 is also less than 23. So you're moving like you have two negatives basically. You can be creative on your own time. It's my domain. Good question. So what do we think? Seems like the majority have gone for 225. But this is not a democracy. But they're correct in any case. So the idea is as the temperature, so the derivative is negative, right? So as I move to the right, that would mean my function is like my cost is decreasing. So as the temperature goes up around 23, the cost would decrease. But since I'm doing this for when the temperature is 20, which is less than 23, I'm moving to the left. So if I have a function that's decreasing, as I move to the left, the y value goes up, right? So our estimate for 20 would be basically I move left 3 units in terms of temperature. So I'd move up 3 times 0.05 units in terms of dollars. Okay, so 225 would be our estimate. All right, so we're just using the linear approximation here to do it. We're looking at the derivative at a given point and sort of assuming the function's more or less linear around that point. So we just move over over 3 up 0.15. All right. So you could get this by computing the tangent line to the curve at 23 as well. Okay. So now we want to find the equation of the tangent line, and it's basically doing the exact same calculation as we just did. All right. So to find the equation of a line, you need two things. You need a slope and a point. All right, so what would be the slope of the tangent line to the graph of f at 23? Good, negative 0.5, right? The slope is just the derivative. The slope of the tangent line is equivalent to the derivative. So the slope at t equals 23 is the same thing as f prime of 23, which in this case is negative 0.05. All right, the point, I just do this, stop this. The point is, well, the independent variable is the t coordinate, and the dependent variable is the function. So this will be 23, and then whatever f of 23 is, which is $2.10. Okay, so now the equation of a line, y minus y naught equals m times x minus x naught. This is point slope form. We just plug these things in, where you plug in 2.10 for y naught, 23 for x naught, and negative 0.05 for the slope. So you get y minus 2.10 equals negative 0.05. And then really it should be t, since this is a function of time. So t minus 23. Okay, and rather than call it y, this might be a little confusing, but we're just going to label this L of t for linear, to indicate that we're using a linear approximation. So our linear approximation to the function L of t is negative 0.05 t minus 23, and then I add the 210 over. So this is just the equation of the tangent line to this function at 23. All right. So how do we find L of 20? Well, we just plug 20 in, and it's the exact same thing we did in part B. So L of 20, this is our approximation to the actual to the actual cost when the temperature outside is 20 degrees. So we use the tangent line at a point that we know about to estimate it. So L of 20 is just negative 0.05, and then I plug in 20 for t. So I have 20 minus 23 plus 2.10, and I get the exact same answer that we got before. $2.25. Indeed, indeed. All right, so this is the idea of a linear approximation. So if I'm looking at a smooth function, and if I graph the tangent line to a given point, and the more and more I zoom in, so if I'm looking at the tangent line at 5, the closer and closer and closer I get to the curve at x coordinate 5, the more the tangent line will just sort of look like the curve. All right. So if I want to know what the function's value is at 5.1, I could use the tangent line to approximate that. All right, so this approximation is better the closer you are to the tangent line, or like to the point where the tangent line is measured, and it's worse the farther away you are. All right, so now we can write this down generally. So let me scroll up so I don't give away the answer exactly. Finding a general equation to the tangent line to y equals f of x at the point x equals a. So again, for a line, you need to write down the equation of a line in point slope form, you need two things. You need the slope and the point. And we've kind of done this several times now. The slope, so what is the slope of the tangent line to y equals f of x at the point x equals a? It'll be a kind of general thing. Right. The slope is f prime, and at x equals a, it'll be f prime of a. Good. Okay, the point itself is just a f of a. All right. So the tangent line then is y minus f of a equals f prime of a times x minus a. Okay, and when we're using a linear approximation, we don't really write, we normally don't call it y, we call it L of x or L of t or whatever our dependent variable is. So if you just add the f of a over, you get y equals f of a plus f prime of a times x minus a. All right, and then you just, instead of calling it y, you call it L of x, and this is the linear approximation to f at a. Okay, so the idea is maybe maybe I know the value of f and f prime at a given point. I can use the tangent line to approximate the value close to that point. All right, and we'll do that. We'll see how we can like estimate certain square roots and stuff like that on the next page. Yeah, basically, the linear approximation really just means using the like writing down the tangent line. Okay, so we'll see how to do that in the next example. So suppose we want to use a linear approximation to estimate the following square roots: 3.996 and the square root of 4.2. All right, so we need to come up with a function that would kind of look like this and a point that would be close to these points. All right, so if I want to estimate the square root of 4.2, what function do you think I might use? Right, I'll just use the square root function, basically. I'll compute the tangent line to the square root function at a point that I'm familiar with. So for example, the square root of 4 is 2. That's a rational, I mean, it's an integer. So I can use sort of 4 as my base point and the square root function. All right, so the function we use will be the square root function. Okay, and the point we use will be 4. All right, I'm choosing 4 because it's close to 3.996 and 4.2, and it's something that I know, like I can evaluate the square root of 4. I can evaluate the derivative of this function, like when a is 4. It's something I don't need a calculator to use. All right, so I'm going to split y'all into groups in a second, and I want y'all to just try to write down the linear approximation to this function at 4. So you're really just writing down the tangent line to that point. Oh, thank you. All right, so I'm going to break y'all into groups, and I just want y'all to write down like what is L of x. What is the linear approximation? And you're approximating it around 4, around when a equals 4. So let's get back together. So I wanted y'all to write down just the linear approximation to this function at 4. So a linear approximation will depend on the function and the given point. All right. So you can see it above me, but I'll just write it again. L of x is the value of the function at a plus the derivative of the function at a times x minus a, where a is the given point. All right. So we have basically everything we need. We maybe don't quite have f prime. What is the derivative of f? So f here is the square root function. Yeah, good. It's 1/2 times the square root, right? And yeah, if you plug in 4, you might get it like an actual value. All right. So L of x is the first term is f of a. So our function is the square root function, and the actual point that we're sort of approximating nearby is 4. So it'll be square root 4, and then maybe I should write f prime of x is 1/2 square root x. So plus f prime of a, which is 1 divided by 2 square root 4, and then times x minus a, which is x minus 4. Okay, so simplifying this, we get 2 plus 1/4 x minus 4. Okay, so this is the linear approximation to the square root function near 4. All right, so this is just a straight line, which is tangent to this curve. See if I can zoom in. Maybe draw a little better. Probably not. So pretend this is a straight line. All right, the teal or blue line that I just drew is this approximation. Yes, perfecto. Okay, so if I want to approximate, say, the square root of 0.2, I'll plug 4.2 into L. So if I want to approximate 4.2, I plug in the value 4.2 into my linear approximation. So I get 2 plus 1/4 4.2 minus 4. Okay, and this is, let's see, 2 plus 1/4, 4.2 minus 4 is 0.2. So you get 2 plus 0.2 divided by 4 is 0.05, and you get 2.05. Okay, so that value, 2.05, is the y-coordinate on this tangent line for x-coordinate 4.2. All right, and we're obviously it's not the same thing as the actual square root of 4.2. It's an approximation. Okay, so based on this picture, did we overestimate or underestimate it, the actual value of the square root of 4.2? Good, we overestimated it, right? Because our tangent line lies above the curve. All right, so we'll look at that again in a couple questions, but you can basically tell if you're overestimating or underestimating by the concavity. So if you're concave down, the tangent line will lie above the curve. So you'll be overestimating. If you're concave up, the opposite happens. The tangent line lies below the curve, so you're underestimating. Okay, it's a pretty good approximation though. The actual value of the square root of 4.2 is 2.049, and then there's some other terms after that, but it's quite close. Okay, and you could do the same thing for 3.996. All right, and in the solutions that I post, it'll be written on there as well. All right, so now let's find the linear. Now let's do something similar. So f of x is sine of x, and I want to approximate sine of 0.1. Okay, so like to do these, like you could probably guess what function we'll use. We'll use sine of x since I'm trying to approximate sine of 0.1. All right, what a value should we use? So like what point should we use? The point you're using should be something that you know how to evaluate. Right, 0. I know how to evaluate sine of 0, right? I don't need to look, I don't necessarily need to like plug that into a calculator or anything. It's a known value. So sine of 0 is 0, so that will be sort of my base point for approximating. All right, so if we want to write down a linear approximation to sine near x equals 0, it'll just be L of x equals sine of 0 plus the derivative of sine evaluated at 0. So what's the derivative of sine? Cosine, good. Okay, and then times x minus 0. So all I'm doing is translating this this expression into like using sine for f and now cosine for the derivative. Okay, so why don't y'all try to finish evaluating this and get and try to approximate sine of 0.1. All right, so you really just have to evaluate all these terms and plug in 0.1 for x. Okay, so a lot of y'all are saying that the approximation to sine of 0.1 is just 0.1. Okay, so we've actually used basically what we're sort of rediscovering here is an approximation that we've used before several times. So does anyone remember, like we've approximated sine for when the angle is near 0. Does anybody remember what we called this? Good, the small angle approximation. So we're basically just reaffirming this small angle approximation that we've actually used already. Okay, and you're right. So sine of 0 is 0. Cosine of 0 is 1. X minus 0 I could just write as x. All right, so the linear approximation is just x. Yeah, we did it using limits. So we would say the limit as x approaches 0 of sine of 2x over 2x. This just looks like 2x over 2x, so it's just 1. Okay, so all right, are we underestimating or overestimating? All right, can you answer this question without using a calculator? So think about what is, you don't have to really know so exactly the value is, but try to think about what is the second derivative of our function at point 1. So our function is sine. So think about the graph and think about whether it's whether the second derivative would be positive or negative at point 1. Mm-hmm. So you could also, I mean, you could look at the graph too to determine, you don't like necessarily have to compute the second derivative. You can also think about the graph of sine. What does the graph of sine look like? Okay, good. So most people have said overestimate, which would be correct, and probably actually the better way to look about this, to think about this, is just to look at the graph. Okay, here in red, or shows up as orange on my other screen. But in red, we have the graph of sine, and then if the linear approximation is just L of x equals x, really enjoying these colors. Then if I try to use this linear approximation to approximate sine, and I plug in a value that's a little bit to the right of 0, my tangent line will lie above the curve, right? So I'll be overestimating. Okay, you could also think that the second derivative will be negative around like close to 0.1. All right, so the second derivative also kind of tells you whether you're overestimating or underestimating. Okay, so now the last topic will be differentials. So we'll use, so this is similar to linear approximations. It might seem a little weird at first, but the idea is that we'll estimate a change in a function, or like we'll try to figure out like how much does a small change in your independent variable change your dependent variable. So if I'm measuring um, like the sides of a box, and I know that my measurement has some error associated with it, maybe like plus or minus zero point 0.1 centimeters. How does that translate to like the error in my measurement for the total volume of the box or something like that? Okay, so the idea is that we're basically just kind of like rewriting some basic notions of derivatives. So we've had before, we say dy over dx is another way of writing the derivative. So we can estimate the change in y by sort of solving for dy. Okay, so you think of dx as a small or approximate change in x. And dy as a small or approximate change in y. Okay, and that's how these are related. All right, so let's approximate the change in volume of a sphere when its radius changes from 5 to 5.1. Okay, so the volume of a sphere is 4/3 pi r cubed, as you all know. As you all love to know, I'm sure. And now let's approximate the change in volume if we know the change in radius. Okay, it's not like really all that dissimilar to some of the related rates problems that we've done. Okay, so if I take the derivative with respect to r, what do I get on the right-hand side? So what's the derivative of 4/3 pi r cubed? Good, 4 pi r squared, exactly, right? If you just use the power rule on the r cubed term. You bring the 3 down, it cancels out with the 3 in the denominator, and then you're left with r squared, and the pi and the 4 stay the same. So we have 4 pi r squared. Okay, so now you can sort of like quote unquote solve for dv. I'm trying to approximate the change in volume given a change in radius that I know. So you sort of solve for dv by just multiplying the dr over. Okay, so if we want to approximate the change in volume when the radius changes from 5 to 0.1, we'll use r equals 5 and dr equals 0.1. Okay, and we'll plug this sort of data into this equation to estimate dv, the change in volume. So we just have dv equals 4 pi, and we plug in 5 for r, times dr, which we take to be 0.1. Okay, so this ends up being, let's see, 4 pi times 25 times 0.1, which is just 10 pi. 4 times 25 is 100, times 0.1 is the same thing as dividing by 10. So 100 over 10 is just 10. All right, and this is in feet cubed. Okay, so I prefer to think of this as like, say I'm measuring a sphere for whatever reason, and I measure the radius to be 5. But I have to take into account that my measurement's not perfect. I assume maybe that there's a like up to a 0.1 foot error in my measurement of the radius. What then would be my, like, how does this error propagate when I'm calculating the volume? Okay. And what we found here is that if my radial measurement is off by possibly 0.1, my volume measurement could be off by as much as 10 pi cubic feet. Okay. So that's how I kind of like think about these differential problems. You're sort of trying to compute a propagation of error. All right. We don't have time for the bonus, but it's basically the same problem. And again, I'll fill that out on the sheet that I post later. Okay. So that's all for today. No need to apologize, I suppose. All right. So that's all for today. Thanks for stopping. I will post this sheet later. On Wednesday, we'll start antiderivatives, which I know we're all very excited about, me in particular. And I'll have office hours from 4 to 5, and I'll be in like the main room, I guess. So it won't be in here. Yeah, you can think of differentials as kind of like measuring like a margin of error, or like how one quantity changes with respect to another. Yeah, Sam, I'll be in the um, doing office hours in the other room, in like the main 180 room. So you can ask me some questions there. Okay, so you could ask here. uh, let's see, I can maybe bring it up. Oh, one sec, I'm gonna bring up the homework. Correct, that's right. So Sam, if you're still here, I could try to answer some questions quickly, or we can always converse via email as well. So there are weekly modules uh, that will be due Saturday at midnight, starting this coming week, that replace your midterm and finals. Okay. So if you plug in infinity, you get infinity to the 0th power. So you want to call this something. You normally like call it L. You take the natural log. So did you get to something like this, Sam? All right, so then when you take the derivative, So this goes to infinity over infinity. All right. So when you take the derivative, the top will be 1 over e to the x plus x. Then using the chain rule, you get e to the x plus 1. And then the denominator is just 1. Right. So yeah, exactly. So now what does it look like when you let x go to infinity from this form? Mm-hmm. And then you just take the derivative. So then you'll just use L'Hopital's rule again. And then I think you have to use it one more time. But I think you should get like 1, basically. So infinity over infinity. Then if you take the derivative again, you'll get e to the x over e to the x plus 1. Right. So this will be infinity over infinity. Do it one more time. And then you'll just get e to the x over e to the x, though, this is infinity over infinity, but they're the same term, so you can cancel them out. And you can basically just say that e to the x over e to the x is 1. Mm-hmm. Yeah, and then you're good, right? No, this is so right. So you do get the limit as x goes to infinity is just 1, but that's not your final answer because you took the natural log of L to begin with. So you have the natural log of L is 1. Which tells you that L is E. Mm-hmm. No problem. Yep.